Hello students, in this second lecture of mechanics of material we are going to talk about the very basic terminologies known as stress, strain, their formulas and how we are going to use and calculate these quantities. And also we are going to have a look at an example of tensile loading. Without further ado, let's start. So starting with the concept of stress is the force per unit area. So the force applied, F, divided by the cross section area. For example, if you look at this figure, we have this cross section area. It is given as 0.05 meter square and force of 500 Newton is applied. Okay, so when you have this much force applied on a certain cross section area, so we calculate the stress. It is represented as a sigma, which is defined as the force per unit area on and the units are Pascal. You can then, if it is quite large in Pascal, you can convert it into megapascal, which is actually 10 raised power 6. Okay, so either you use Pascal, megapascal, it's totally up to you. Now there are, for example, we have a tensile stress and compressive stress. Tensile stress is as shown in this example, where forces are trying to pull the body apart. So there is tensile stress, but in other words, if for example the forces are inward and trying to compress the body, that will be our compressive stresses. In this case, let's see what is the applied stress. So using the formula that we have, so sigma is equal to force divided by area. So force is 500 Newton and our cross section area is 0.05, so that is Newton. This is meter square. Okay, keep in mind the units as well, and it will give you something like I think 10,000. Yeah. Okay, so that will be 10,000 Newton per meter square. Just to confirm, I will use a calculator here. So we have 500 and then divided by 0.05. Okay, so you get 10,000. This is the stress value applied on this body. Does that make sense? I hope so. Okay, so this is the very basic idea of what stress is. Let's talk about the second quantity, which is strain. Now strain is deformation per unit length. Okay, so it is the change in length divided by the original length. Okay, so for example, this rod A is shown here. The original length is L, but after applying the force P, okay, when we apply a force P, we get some change in length, which is here represented as delta. Okay, here it is represented as delta L, so whatever you represented, it will just be consistent. Okay, all right. So our strain formula is then either, here it is delta, so it is represented by delta or change in length divided by original length, or you can use this delta L divided by L, totally up to you. Okay, since it is pulling it up, so it is tensile stress applied on the body, and the result is the strain produced in the body. Strain is a dimensionless quantity, dimensionless in a sense that you have change in length in meter and original length is also in meter, so your units cancel out and you get no units as a result. Okay, so it is a dimensionless quantity. For example, tensile strain or compressive strain, depending on what kind of forces are applied on the body. Okay, all right, so let's see, we have this example here that says that you have let's say, for example, length of 0.2 meter, the change in length is 0.015 meter. What would be the strain produced in the body? Okay, so let's see, your change in length is 0.015, okay, meter, and divide by your, this is the change in length, this is the original length, so original length is 0.2, and you get the strain is equal to, strain is by the way represented by this epsilon given here. So let's calculate it. So 0.015 divided by 0.2, so we get 0.015, oh sorry, divided by 0.2. Okay, so we get the strain of 0.075. Okay, so this is the change in length divided by original length. What you get is 0.075. That's the value of strain that we get from by applying the force on the given rod. Okay, so very simple. We talk about stress. So stresses are the forces divided by the cross section area, whatever the cross section area is. Strain is the change in length, whatever the change you get, and divided by the original length, that was the original length of the body. Okay, so that will be the strain. Very simple, straightforward. Okay, now there is a relationship between stress and strain. Okay, relationship, I'm sure you have heard of the Hooke's law, where your stress applied is proportional to your strain gained. Okay, now what does that mean? Hooke's law states that bodies are initially linearly elastic. Okay, linearly means it gives you a straight linear line up to a certain point. It's not completely throughout, but up to a certain point these lines are linear. That's what Hooke's law states. Okay, and it says that the stress will be proportional to the produced strain. So you are applying a stress on a body. Okay, you are applying a stress on the body, you will get some strain, and up to a certain limit, okay, which actually we called as the elastic limit, which is, like, for example, shown by this dotted line here. This elastic limit, within the elastic limit, the response shown by the body will be linear. So you keep on increasing the stress, you will get linear strain as a result. Okay, so in this case we introduce elastic modulus that depends on the material. So it's the constant of proportionality. When we remove this proportionality and convert it into equality, we introduce this constant E, which depends on the material properties. So for each material it will be a different value. All right, so this is the equation, that the basic equation that we get for the stress strain relationship. Now we know the stress is force per unit area. Okay, and we also know the strain that we just discussed is the change in length divided by the original length. All right, so once we insert the values there, what we get as a result is a general relationship. For example, if you want to find out the change in length, and you know the elastic modulus of the body, you know the cross section area, you know the force applied, you know the original length, you should be able to predict or actually calculate the change in length by just rearranging these equations. So if you don't know just one value and you know the rest of the values, you can rearrange this equation and calculate the unknown quantity. All right, using this stress strain linear elasticity relationship. But keep in mind, this will be applicable only in this specific elastic limit region. Okay, it will not be applicable outside, because outside it is not linear, it bends and it makes curves. That region is known as the plastic flow region. Plastic means that in this case your deformation is not elastic but plastic. Okay, now let's have a look at this example here, where it states that you have the original length of 6 meter. So it has shown that initially it is 6 meter. The area is also 0.05. You have 5 Newton force applied, and it's also stated that your elastic modulus is 110 GPa. GPa is actually gigapascal. I think 10 raised power 9. Okay. All right. So the question says that what will be the change in length produced. So so we have to calculate the change in length produced in the body if these are the conditions. So we can simply use this formula. So your change in length will be actually equal to the force 500 multiplied by the original length, which is 6, divided by the elastic modulus. So that is 110 into 10 raised power 9 and then you have multiplied by the area. So area is 0.05 meter square. Okay, so you just make sure the units are the same. Okay, so it should be in meters, this must be in newtons, and then this must be in pascal. Okay, so I converted from gigapascal to pascal, that's why I added 10 raised to power 9 here. Okay, all right, now let's calculate this and see what the answer is that we get. So we have 500 multiplied by 6. Okay, so we get 3000. Now divided by 0.05. Okay, so you get 60,000. Again divided by 110, and okay, and then divided by 10 raised power 9. Okay, so we get something like change in length, a very less change in length. Obviously, when you apply only 5 Newton force on a body of elastic element that is quite large, you are not going to get much of a deformation. So that is something like so 5.4 10 raised to power minus 7, that is something meter. So this much of deformation we are gonna get. Even if you talk about in millimeter, that would be something into 10 raised power minus 4 millimeter. Okay, so this is what you are gonna get as a result of the change in length of the, once this much forces are applied with the elastic modulus of 110 gigapascal, your original length is 6 meter, and then your cross section area is 0.05. So this is just to understand that if we know all the quantities and we don't know one quantity, for example in this case we did not know what will be the change in length if these are the conditions, so we can simply use the relationship to get the results. Okay, so mechanical behavior very briefly. When you have a material, we did talk about the elastic deformation, that it deform linearly in this region, so you will have a straight line in this region. Okay, and that is why we call it the elastic deformation, because in this case the stress is proportional to the strain, so it is elastic. Now in this region the body should be able to return to its original position. For example, if you have a spring, okay, and you deform it, okay, you extend it within this region, the strain is within this region and stress is within this region. Okay, so your stress and strain are within this region, the body should be able to return to its original position without any problem, okay, after releasing the stress. And this, up to this point, it will give you a linear results. Okay, so that's why we call it proportional limit, because it is according to the Hooke's law, where stress is proportional to the strain. Beyond this limit, up to the yield point, you are still in the elastic deformation region. Okay, that means that if you release the stress, the body will be able to return back to its original position. Okay, so within this region, even it is not linear, you are still able to return the body to its original position after releasing the stress. Okay, so up to this point, which is actually known as the yield point or fully reversible point, so below this point it says that the body is fully reversible, so you can, if you release the force, the body will be able to return to its original position, okay, without any problems. But if you cross this limit, okay, you go above the yield point, that is your plastic deformation region, which means that once you are in that region, the body will be fully deformed, not fully deformed, but in a sense that it will not be able to recover itself to its original position. So you, for example, you are keep stretching this spring, there will be a point that once you release the force, the spring will be something like very opened, it will not be as congested as its initial case. Okay, so it is now entered into that plastic deformation region. It is not able to come back to its original position. All right, so that is what the plastic region means. Now there is a term there, this plastic region is divided into 2 points. Okay, so at the top we have the ultimate strength. Ultimate strength means it is the maximum stress that you can apply on the body. Okay, after this stress, the body starts to this is the ultimate strength, or this is the maximum limit. And if you see, this region says strain hardening. Okay, so that means that the body is moving in a path where your strain is comparatively less to the stress. Okay, so it's not less, but in a sense that as it was coming earlier, it is not in the same route. Okay, so you are getting strain hardening, which means the curve is now moving up. For example, here your curve is something like this, but after this region the curve goes up. Okay, so your strain, comparatively you are getting less strain than you were getting before. Okay, which was, in this case, it is supposed to come here, but now it is going here. So your strain is comparatively less to the what you were getting earlier. Okay, so that's why we call it strain hardening. Okay, and ultimate is the maximum strength that you can get from here. Okay, after you reaching the ultimate point, the body will, even you don't need to apply any extra stress, and it will start deforming, increasing the stress again. This phenomena occurs called necking. Necking is when you are trying to stretch a body and it starts to produce a neck here. Okay, it starts to produce a neck means that it gets narrows down, because you are applying multiple forces here in opposite direction. You are trying to pull it, so it starts to create a neck here, which is actually results in the rupture or fracture. So that means it's very possible that at the neck region the body will fracture. Okay, so this is the whole behavior or mechanical behavior of the material if you are applying certain stresses on it. So we talk about the stress. There is the limit for the, let's see, so you talk about the limit, proportional limit, that is linear. So that is the first point. Then we talked about the yield strength. Okay, that is the, up till this point the body is fully reversible. Finally we move on to the ultimate strength, which is which states that the body is having this much of maximum stress. Beyond that you cannot apply, because once you achieve this one, the body will start to deform itself and create a neck. At the end it will get fractured. All right, so I think that is clear. Here is an example of what necking means. For example, if you look at this body, this is actually this one is the top part, and this is the bottom. So this was once a same material. So this was attached here. If you can imagine, this was attached on the top, and you see this body start to shrink here, creating a neck, and then actually breaks up. Okay, so these are the two damaged regions which are actually split apart. So this is in case of ductile material. Ductile materials actually give you this full curve of that we just discussed. So it gives you the linear, it gives you the linear limit, it gives you the yield strength, then it gives you the ultimate strength, and finally it goes to fracture. But in case of brittle material, what we have is we only have the linear, and then at the yield strength we are small strain, at a very small strain, because it does not go beyond this point for the brittle material, and it just break. For example, see, there is no necking in this case, so you don't see the region shrinking. Like for example, in the previous case you see the neck created. In this case there is no necking region. The brittle material just breaks when it reaches its yield limit. Okay, so that's the difference between the ductile material and brittle material as well, and how they mechanically behave. Where your ductile material has quite large strain, brittle material breaks at very small strain. Okay, I hope this makes sense, and this is the end of this lecture. I'll see you in the next lecture. Thank you. Take care. Goodbye.